Very good morning to all of you. Now I have creating a video to demonstrate how to implement a Verilog code into an FPGA. Okay, so let me first connect my system. Our labs system I have connected. Now first let us start the tool. We are going to use a tool called as Vivado. Xilinx is the company which is providing the software. So I am going to start the software. Now, I hope you are able to see my pointer here. I will click here, create project. Now your new dialog box has opened. Click next. I'm going to create the name of the project to be experiment 1. And I will click next. I'm going to create an RTL based project. RTL stands for register transfer logic. And here I'm not going to anything. I will just click next. Here also I will not going to do anything. I'll just click next. And here we have to select what board we are going to implement. So I will select here boards. We are going to implement in the Z board. So I will select the Z board. So I will repeat it. Board, Z board, then click next. Okay. So this is a summary of the project. Experiment 1 is the name of the project. It is an RTL based project. I have not added so far any source file or constraint file. This is the board. It's what we have selected. Okay. I'm creating the project now. We have to wait until this updating has been done. Now the project is created. And you can see again here in the project summary dashboard for experiment 1 where it is created, name of the board, all the details are available here. I hope I am clear for you all right now. Now I have to add the source file, everything I have to add now. Now here I hope you are able to see in the source tab, here you are having plus symbol. Click here plus, or here also you have add a source. Either you can click here or this plus symbol also you can click. Here I'm going to use now plus symbol. Now I'm going to add or create a design source. Okay. And I'm going to click next here. Here only I'm going to add the source file. I'm going to just click here, create. Verilog is a language I have chosen now. I'm going to implement logic gates. All logic gates in one program I'm going to implement. And I'm click next. This is a new source file. What I'm going to file name is logic gates. Okay. And so you see here logic gates.v is the name of the module what it has created. Okay. And now again module name it is asking. I'm going to keep the same name as logic gates. And just clicking OK. File name logic gate. I have created the module name also logic gates. And I'm going to click yes. And wait for some time. Okay. Here the file has been created in the design source file logic gates and the name of the module is logic gates.v. Click here. A new tab is created here. You can see module, end module, and the name of the module is logic gates. I hope you are able to see that. Okay. If not, I will choose a magnifier. I hope you are able to see now here module logic gates. Okay, now I am going to write the program for this logic gates where I'm going to implement all logic gates and or NAND, NOR, XOR, all things in one module, which covers all the modules. Okay, how to close this magnifier? Okay, I will close it off here. Now I will open my manual what I have already shared to you. So this is my program from the manual. Okay. Where here actually the name of the module is logic underscore gates, but I have created as logic gates. So let us not bother about the name of the module. I will copy the other contents of the program. Okay. Input is A, B and output other things are, I have defined it here like this. So I am going to copy the input and output variables over here. And let me close it off here. Here there are two open braces are there. Let me have only one thing. And then let us copy the other lines of the code also. Copy. I will place it here. So this 4, 5 and all line number, that is not a mandate here. That is going to create unnecessary confusion. So I am going to just same program where y is equivalent to, again I will use a magnifier. You see, this module has 1, 2, 3, 4, 5, 6, 6 outputs and 2 inputs. Okay, y underscore and is output which is equal assigned to a ampersand of b. She is going to do the logical AND operator first line here. And this is second line is going to do the logical OR operator and it is assigned to the y underscore R output. Last one, third one is complement of A. Next one is A XOR of B. This is A and B and negation. So it is an AND operator. A, A or B negation operator. So it's an OR operation. So this is the Verilog code, very simple logic gate program I have written here. So once you are done with the code, you have to check whether this program is running as per your desired functionality or not. So you have first created the source file. Now I am going to create a going to check whether the software is program is running as per my requirement or not. So I'm going to run the simulation, run behavioral simulation. I'm going to do now. Okay, fine. Now you can see the pointer where I am pointing the A, B and the output variables are available here. You see here, if you are not able to see, I will use a magnifier once again. The inputs are A, B, Y underscore and Y underscore R, Y underscore not, Y underscore XR, Y underscore NAND and Y underscore R. So these two are the inputs, the rest of them are outputs. Now I have to provide inputs to this particular 1 minute, I'll close the magnifier. I will provide inputs to A. For example, now select the variable A here, right click and force constant here. And here you select here binary 1 by a force value of 1 and then click OK. Now I will give force value of force constant binary 0 and click OK. So what I have given A equivalent 1, B equivalent to 0 I have given. Let us run the simulation here. So I have right click the variable. I will do it once again. Force constant I have given and here I selected the binary and I gave the value here 1. Once again I am giving it for your convenience. So you after defining A and B, you go here. I hope you are able to see the pointer where I have chosen here. Okay, I will go for once again magnifier. Go here and select this button. Okay, for run for 10 microseconds. It will continuously run the simulation. It will run for 10 microseconds alone. It will run the simulation. Now I will close it off and I will click this button. You can see that the output is executed for first 10 microseconds. I will click the pointer here. You see here for the binary value of A equivalent to 1 and B equivalent to 0, indicate 1, 0 will give the value of 0, OR gate will give the value of 1, not a complement of A. So here 1 na, here it is equivalent to 0. And here XOR na 1, 0 combination XOR will give the value of 1. And na for this combination, I'm getting the value of 1. NOR gate, I'm getting the value. So all the inputs are verified for the input combination of 1, 0. Now this is one way of providing the inputs. But if I want to provide continuously, it's like a waveform I want to verify. See here, for example, 2 inputs, you can verify 0, 0, 0, 1, 1, 0, 1, 1 combination. I can provide the inputs and verify. But think about if I'm having 4 input variables are there, A, B, C, D, 2 power 4 equivalent to 16 combinations will come. So that is 16 times you have to give force constant, force constant, force constant. Think about if you are having 5 variable, you have to give 2 power 5 equivalent to 32 combinations you have to provide. So you have to give force constant itself 32 times you have to give and check the output. So what can I do is the other way is that I will restart the simulation once again. I will start from scratch how to give the simulation. See here now I will select the variable, right click instead of force constant. Now I am going to choose force clock and select here binary 1 0, leading edge 1, falling edge 0. Let the period of that cycle be 100 nanoseconds. One signal I have selected. Every time it will switch on and off for 100 nanoseconds. The period of the clock cycle is now 100 nanoseconds. Now similarly, I will select one more another input signal B. I will select as force clock. I will select here binary, leading edge 1, binary, falling edge 0. Now for A signal, I gave the period to be 100. Let me now here give the signal to be around 50 or 100. Some other signal I will give and I will select here. So the period for A is 100, period for B is 50. That you can change. Now for ease of convenience, I am selecting here 50 nanoseconds is the period for the B signal. Now I have given the inputs. Now the next thing is that I have to, you are not supposed to give the force for other outputs. You can give force to only the inputs of the signals alone. After providing the inputs, run the simulation for 10 microseconds. So the signals are generated based upon the input what we have given. Now click the pointer. The yellow color line is the pointer and click zoom over here. Now you see here, move the pointer here. The inputs is 1 1. If I move the pointer here 1 0. Now here 0 1. Here 0 0. So all 4 input combinations are available here and is given to the logic gates, whatever we have designed, and we are simultaneously checking all the logic gates at one instant. Of just one click, we are able to check all the combinations of logic gates. It is verifying, and we have created this logic block here. Okay. Okay, and now the job is done. We have verified the program is working fine. Now we want to check what is the circuit the program has been created, because Verilog is an HDL language, hardware descriptive language. I want to check whether it is creating the hardware correctly or not. So after checking the simulation, I am going to do the RTL analysis. Under the RTL, you can see here in the just one tab below it is open elaborate design. Click over there and click here elaborate. Click OK. It will read the netlist and it will create the circuit diagram for you based upon the program what you have created so far. Now you can see that there are only 2 inputs and all the outputs are created. And this is the circuit diagram what the program has been created so far. Okay. We have verified the simulation. We have created the circuit diagram. Now I have to implement it in the Z board. What I have to do now, next you have to run the synthesis and the implementation. See here, here you no need to remember or by heart anything, how to use the software. I am going just one step below the other step. First creating the source, then running the simulation, then RTL analysis we have created. I am going to synthesis this design and implement the design finally bitstream generation. One tab just below that. We have to go one step below every after completing the previous step. Now I will do run synthesis, click OK. So after verifying the simulation and creating the circuit diagram by the software, RTL has been created. Now I am running the synthesis. You can see in the top right corner, I hope you are able to see my pointer run synthesis design. It is completing the synthesis process over here. Once the synthesis is getting completed, it is asking for run implementation. Okay, next step is run implementation, which is the next step of the implementation procedure. So it is directly pointing out to run implementation. And here I am going to select OK. Click OK once again. Now it is initializing the design and it is going to create implementation is going to get started from now on. We have to wait until the implementation has been completed. Okay, now the implementation is successfully completed. Open implemented design, it is asking. Click OK. You want to close the elaborate design, okay, yes. The circuit diagram will get closed out. Now you can see here package device are there. Now if you see what is the device now here, this is the entire FPGA IC sitting inside the Z board. If you see here, this portion is a PS portion, processing system, and this portion is a programmable logic. This block, all things are programmable logic block, where if you are writing a Verilog or VHDL program, it is going to be implemented in this portion only. Here, this is an PS part. PS and PL are the two portions of my FPGA, where PS portion I have two ARM Cortex processor are sitting out there, and the rest of the portions are programmable logic. Sir, what is there inside the programmable logic? Now you click and zoom over here, and you can see some many modules are available over here. Okay, what are these modules? Now you can see here, this is a slice. Inside the slice, there are combinational. This is one combinational logic block. This is other combinational logic blocks. Inside the combinational logic blocks, you have multiplexer, lookup table, encoder, decoder. All these combination blocks are already sitting inside that. So like that, you see how many such rows and columns are available. So what is actually happening now when you are writing the program? These modules are so intermediate wires are there actually in between the CLBs. Here there will be wires will be running here, vertical and horizontal vertical wires will be running. They are getting interconnected based upon the program whatever you are writing it. Okay, so it's like a reprogrammable logic. So these blocks are not getting changed. They are getting interconnected to implement your function. That is what actually happening over there in an inside an FPGA. Okay, so now our program, I will try to show you. This is our where is it? Yeah, in the net list you can see the nets and leaf cells are available. And here I hope once I select it here, some few portions are getting selected. You can see that this is where our program is going to use only these many blocks only it is going to use for our program. So out of this so many resources available, my program is very simple block. Okay. Now after running the synthesis and implementation, here actually it will be in layout and default layout. Now you have to change it to IO planning mode here. Please make a note after simulation and synthesis and implementation, you have to change this tab to IO planning. Once you see here, first I will change it to default layout. Here, what are the tab you are seeing here? TCL console, message, log, reporter, design role, power, DRC, timing are showing here. Now, once you change it IO planning alone, you will see here IO ports that a tab will be created. So make a note here. You have to change here to IO planning. Then only you will see the IO port option available here. Once you select that IO port option, you can see all the input pins and output pins. So here I have two input pins and all the output 6 output pins are available here. Now you see here, actually my program is sitting here inside the IC. But how I can provide inputs A and B to the inputs of these logic gates, common inputs to these logic gates, and how I can verify the output Y underscore and Y underscore R, all these things, where should I see it? In your digital trainer kit, you are giving input A and B and you are seeing the LEDs are glowing there. But here, how I can check the output, provide the input, how I can take the output, where I can observe the output. For that, you have to first see what is the, I just searched for in the, I hope you can see once again. I will just come out. In the internet, I searched for ZED Board user guide. First link by the Digilent. I am just clicking over there. This is the image from the user guide I am seeing here. Now in the, this is a Z board what we are using in our lab actually. Here is the power cable. This is the cable where I mean there are USB cable port from the computer should be connected to the programming pin over here. So here you can see program PROG. So power cable and programming cable should be connected here. And you can see here the switches, dip switches are there. 1, 2, 3. So there are 8 switches are there. And here you can see that small LD0, LD1 represents the LEDs available in the board. So I'm going to use these switches for providing inputs to my AND gate, OR gate, or whatever is the logic gate. So I'm going to use only 2 switches here and 6 LEDs to absorb my outputs over there. So you can see here SW0 represents the switch 0, SW1 represents the switch 1, SW3 represents the switch 3, and LD0 na LED1 like that. There are switches are there. And adjacent to these switches and LEDs, you can see there F22, G22, H22, F22. These are the pins available in my. In order to access this switch, this pin I have to choose here. In order to access this switch, I have to select the pin number G22. Like that, I have to select it. But where do I select it now? Now you go to the software. In the input pin, you see the switch. Where is the switch? SW0. If I'm going to use this switch, now I have to select the pin number F22. So I will select here pin package pin F22. I will select. Okay. And what is the second input? G22. So I will select here G22. I selected the inputs. Now I have to select the outputs. What are the outputs I have? LED 0 not T22. I have to select T22 and then T21. Second output is T21. Next one U22. So U22 followed by U21. U21. Okay. And then followed by V22. V22. Then followed by W22. W22. Sir, do I need to remember these pins for all elements? No, definitely no need to remember. I will just say. So after selecting these pin numbers correctly, you go here in the IO standard, select here LVCMOS 33. LVCMOS 33. For all the pins, you have to select LVCMOS 33. Then select here LVCMOS 33, LVCMOS 33. Both input and output, select LVCMOS 33. Then press Control Save. Control S, you click. Okay, I'm going to save the file. Control S, if I click, this tab will open. Click OK. And I'm going to choose logic gate itself, name of the constraint file. So there are 2 files we are creating here. You go there and check what are the 2 sources now. One is a design source and other one is a constraint source. Logic gate.v is the design source name, and the constraint file what we created is a logic.xtc. What is there in the logic.xtc? Now you see here pin number A, F22 is assigned to the A input of my circuit diagram. G22 input pin is assigned to the port B of my module. And other pins are connected to the T22, T21, W22 like that I have created. And all things are assigned with the LVCMOS 33. So that is whatever I created in the IO port and IO planning tab, that is created like a set of instructions, whatever I have created. That is a constraint file. Now, what are the 2 files I have now? I have the design file and the constraint file. Now, next step is that I have to dump it in the FPGA board. So the logic design file, constraint file, both should be converted into bitstream file like ones and zeros. Then only I can implement in the FPGA board. So what should I do now? After implementation, click here. So now what are the steps I have done? Source created, simulation checked, circuit diagram created, RTL circuit diagram created, synthesis implementation we have created. Now I am going to generate the bitstream. Bitstream is a combination of design file and constraint file. It will be clubbed together, converted into a binary file. It will be created suitable for dumping it in the FPGA. We have to wait until the bitstream has been created. Okay, now you can see that bitstream generation successfully completed. Click OK. Okay, so now your bitstream is ready to be dumped here. So after generating the bitstream, you have to go for Open Hardware Manager. Go there, click the Open Hardware Manager. Now it is showing here Hardware Manager device is not connected. Right now, I have not connected the device. 1 minute, I will just connect the hardware and I will update you. Meanwhile, I will pause the video. Okay, I will just 1 minute. I will just come. Sorry, I don't have the board right now. Maybe in lab, I will show you how to. So once the device is connected now, you hear the device, that serial number will be available here. Then you have to just click program device. The program will be loaded into your hardware. Okay, so then you can verify by providing inputs to the switches, and we can verify corresponding outputs in the logic gate. Simultaneously, you can check for y underscore r, y underscore r, all those things you can verify. Moreover, while using the board, make sure that you are connecting two wires to the board. One is you have to connect the adapter to this cable, and for programming, you have to use this pin should be connected to the USB, where from the computer, the program will be loaded into the device and it will be loading it over here, and I have to connect to the power supply externally. Muller. And one important information I would like to say is that instead of remembering the content F22, G22, these pin numbers I'm saying that na. So you no need to remember that. You go to internet, search for ZED Board Master XDC, and I am going to click the first GitHub link. If I click that, it is going to pop up to this window where you have the all the pin numbers are available here. Okay, so let me now what are the inputs I'm using and outputs I'm using now. LEDs are the outputs I'm going to use. So LD0 stands for pin number T22. LD1 na LED1 is connected to the pin number of T21. LD2 na connected to the pin number U22. So whatever we have used from the board, the data is available in the master XDC file. Now these are the LEDs, and similarly I have to search for switches. SW0 switches I have to search for. Yeah, you can see here switch 0 F22, switch 1 na G22, like that I can The pin number details are available for each and every peripheral available in the board. Okay. Now, I will try to show you if the board is connected, how that program device will be existing to you. So now I have connected the board. So even after turning on the power supply for the board, near to the power adapter connection, here you have the switch option is there. You have to turn it on. Then here one LED light, where na here exactly power, that LED green color LED will glow on. Then only it shows that your board is connected properly and powered on properly. Now, even though I connected the device physically to the computer, it has not been detected by the software. So what should I do? Click here, open target, try clicking auto connect. Then if the device is powered on and connected to our computer correctly, it has to show here the device is not connecting here. Not connected, auto connect. Oh, sorry, I have to connect it here. Now I hope the device serial number, everything is available now. Now open target. Open target auto connect. Now you are getting the option for program device. Once you are clicking the program device, the bitstream file, what has been created in the previous step is getting the file name logicgate.bit is getting automatically selected. You no need to browse and select them. Click program. The program, the device is now getting programmed. While programming, you can see that near to the this place, the done option is there. No, here a blue color LED will glow on, showing that your program has been successfully loaded into the IC. So this is the zinc FPGA what we are loading here. And if you provide the inputs, the LEDs will glow accordingly based upon the logic what you have created. Now it's your time to check your program in your device. Thank you.